So yeah, my title is Measuring Gravitational Waves in Binary Black Hole Merger Simulations. Particularly, I'm focusing here on extraction and scribe plus higher modes, and also the recent result the extraction of a nonlinear memory effect. So this work is done in collaboration with this gang of people here, with Nigel Bishop, Dennis Pony, Eric Schnetter, and also Bela. Okay, so first I'll do some words on motivation of binary black hole merger simulations. I guess most of you know perfectly about it. Then I will introduce our computational infrastructure, especially the multi-block and AMR simulation code, and then also wave extraction techniques and especially Cauchy-characteristic extraction. And finally, I apply these two ingredients here to measure the nonlinear memory effect in binary black hole mergers. All right, binary black holes, everybody knows what this is. I mean, two black holes, as they inspire, they lose gravitational energy through gravitational waves. We're interested in these gravitational waves. Examples are given by, for example, supermassive black hole mergers or supermassive galaxy mergers. Here are a couple of fancy photographs from Hubble. There are models that predict that, for example, at the redshift z equals 2, that we expect one event per year in these galaxy mergers. So there's, whenever galaxy merges, the center of supermassive black holes also merge. So binary black holes can radiate between 3 and 10% of their total mass, and even though the release energy can be enormous, 10 to the 60 ergs, for supermassive binary black holes, the wave amplitude will still be tiny, about 10 to the minus 21, depending, of course, on the mass of the black hole and the distance. And for this reason, in our gravitational wave detectors, we need gravitational wave templates for matched filtering searches. And also, in the future, crucial for gravitational wave astronomy is the accurate representation of the wave modes, especially also higher modes. Okay, binary black holes proceed in 3 stages. We have the inspiral phase, we have the plunge and merger phase, and the ring-down phase. The inspiral phase can be well modeled by post-Newtonian expansions, and the ring-down phase by black hole perturbation theory. It's only in the plunge and merger phase, which is highly nonlinear, where we need actually numerical relativity to get accurate results. And numerically, you can do that by just foliating the 4D spacetime in terms of spatial hypersurfaces along some time-like vector field. And we have to impose some initial data on the initial hypersurface, and then we evolve that numerically by using supercomputers. And in our particular case, we represent the metric fields on uniform Cartesian grids and use finite difference operators to approximate the derivatives. And we also use adaptive mesh refinement to place resolution where it is necessary, particularly around the black holes where the curvature components are strong. And we treat separately the discretization of space and time by making use of the method of lines, where we first discretize the spatial, the right-hand sides of the equations, and then approximate the time derivatives or perform the time integration by using a 4-order Rodier-Kudder scheme. And in our particular case, we use between 100 and 1,000 processors, and runtime is approximately 1 or 2 weeks, depending on the model, of course, and the resolution. And once you've computed the metric in your spacetime, you're actually interested in extracting the gravitational waves from the numerical spacetime, and then there are 2 common ways of doing that. One technique that is nowadays used relies on psi4. This is a certain y component of the y tensor, and thanks to the peeling property of the y tensor at large distances to the source, the y tensor can be decomposed in 5 different components, and psi4 is one of these, which has the slowest fall-off 1 over r with the distance to the source, and is said to be the outgoing gravitational wave field because all other components approach 0 quicker than psi4. And psi4 can be calculated through everywhere in the space-time numerically during the simulation, and at large distances to the source, actually at an infinite distance to the source, it can be identified, or it can be related to the actual gravitational wave strain that we measure in the gravitational wave detector, this expression here. The other method relies on gauge-invariant spherical perturbations of the Schwarzschild spacetime. We have this approach, we have a fixed Schwarzschild background metric and view and have some perturbations around that. And you can decompose this perturbation in terms of tensor spherical harmonics, and these can be related to even and odd parity master functions that, upon this linearization ansatz for the Einstein equations, obey wave-like equations with a scattering potential, and these master functions can also be computed from the spacetime and later on also related to the actual gravitational wave strain. However, both of these techniques rely on the fact that we can only do that at very large distances to the source, or in fact at infinity. And if you look at the Penrose diagram, gravitational waves will travel here in 45 degrees, originating at the source in the interior of the domain, and at Scri plus, at the boundary, conformal boundary of spacetime, psi4 and also the gauge-invariant master functions can be related to the gravitational wave strain. Unfortunately, our computational domains are finite, which means that we can only simulate a subset here. That means we have to introduce some cutoff because we can't evolve our radiation out to Scri plus. So, because our computational domain is finite, we introduce a finite extraction radius, which are in practice coordinate spheres around our source. So the black holes evolve somewhere here, and at large distances, so with very large radii, we place several extraction spheres around the source. The drawback is, of course, that we have a finite radius that cuts off all the nonlinear dynamics of the far wave zone, especially interactions of the gravitational waves with themselves in the wave zone. And furthermore, because we simply choose here very simple, or usually commonly, what is done nowadays by most groups, is that we have simple coordinate spheres, which means that our waveform that we extract on these spheres can be contaminated by gauge effects. And currently, these spheres have a radius of 100 or 200, I don't know. Villa, for example, what radius do you extract? 300 m or something?
Probably larger, but still a few hundred m.
Yeah. So, and then by placing several extraction spheres on the computational grid, we can use the information to extrapolate, or try to extrapolate the results obtained on these extraction spheres to infinity, and hope that these extrapolations give close enough answers to the true answer that we had obtained at Scri. Another problem with finite domains is that that we have to place an artificial outer boundary at our computational domain. So if here's the source in the center of our domain, and here's the outer boundary, because we don't know constraint-preserving outer boundary conditions, there will be garbage traveling into the interior of the domain at the speed of light, and eventually, after some time, spoil our solution in the interior here. And if we have our extraction sphere at this radius here, of course, the information from the interior domain needs some time to hit this extraction sphere where we compute our gravitational waves, and we would like to have this, the influence from the outer boundary causally disconnected from our gravitational wave measurement on these extraction spheres. And, yeah. So one way, of course, of circumventing this is by enlarging the simulation domain. That would mean that the artificial outer boundary is, of course, further out. Our extraction radii could be much larger. And this would mean that extrapolations would eventually become more accurate, because there is simply larger radius, and as we increase the radius, the answer that we get will be closer to infinity in some sense. And unfortunately, with Cartesian-based codes, the computational cost when we enlarge the domain scales as r cubed, but on the other hand, the the wave zone has spherical topology with a constant angular resolution, which means if we had spherical grids with fixed constant angular resolution, we could enlarge the simulation domain and the computational cost would only scale linearly with R. So for this reason, one could think about multi-block simulations. Multi-block simulations allow one to cover the simulation domain with different grid patches. In our particular approach, we'd like to keep our Cartesian-based adaptive mesh refinement code in the interior domain surrounding the black holes, and we simply want to attach some spherical grids on the wave zone in order to have regular derivatives everywhere. We have to introduce multiple grid patches, and one choice could be, for example, stereographic patches. But because we need to communicate data between these patches, stereographic grids could introduce, because the distortions across these boundaries are rather large, could introduce inaccuracies. So therefore, we rather make use of the so-called 6-patch inflate cubed patch system, which also has the advantage that grid points across the sphere have a relatively homogeneous or uniform distribution. And we make use of interpatch interpolation in order to communicate the data between these patches. And we work entirely in a global Cartesian tensor basis. That means we don't need to transform the tensor components of the metric from one local coordinate to the other local coordinate system. But because the derivatives are still taken in the local tensor basis, we need to apply Jacobians in order to transform the derivatives to the global tensor basis. So we've coded that up, and this scheme now allows us to place detectors at radii 1000 m. That's approximately a factor of 10 larger as before. So before we had about 100 m, between 100 and 200 m, and now we can place detectors at 1000 m that are actually causally disconnected over the time of the measurement of the extraction sphere from the outer boundary, which generates this garbage. At the same time, we have improved radial, angular, and time resolution in the wave zone, and because we can get rid of a number of mesh refinement levels, we have less back reflections from these adaptive mesh refinement boundaries, which in the end results in better accuracy and in the fact that we can resolve higher harmonic modes of the waveforms.
So in the wave zone, will you use a constant radial grid stepping all the way to the outer boundary, or do you portion your grid?
Yeah, so up to our outermost detector, which in this simulation was, we show waveforms for this simulation, was at 1000 m, and all the way to 1000 m we used a radial resolution of 0.64 m, and beyond that we introduced some radial grid stretching over a zone from 1000 to 1500 m, so some smooth transitional region, which stretches the radial coordinates by a factor of 4. So
the reason I'm asking is that these compactification, special compactification schemes, which effectively is what you're using, effectively end up with a coarse grid for that waves have to travel through in a far region.
I mean, until they hit the detector, then we still have the high resolution, the resolution radial coordinate. But beyond that, of course, they will enter this region with de-resolution, and there must be some, of course, because the resolution becomes constantly lower, there must be some back reflection somehow, some smooth back reflection induced.
Do you see the reflection?
Not really. I mean, we have even seen that when we place the stretching right, when we place our detectors right in the stretching region, it barely has any influence on the wave. Of course, it will have influence on higher harmonic modes. In that case, we just initially when we did some testing, we just looked at the dominant L2 M2 mode. So of course, it will have influence in A6 M6 or in L8 M8. The higher you go, the more the influence will be. But
and so your outer boundary is at
In this particular simulation at 3600 M. The outermost detector is at 1000 M, and because the waveform is approximately 1400 M long, over the course of that it's causally disconnected from.
Do you save a lot by increasing the grid spacing by this factor of 4? Because if it just goes with R, it sounds almost to me just keep it at 0.64.
Yeah, but still, I mean it can. You still feel it if the waves are, even though it's evolved every 8 time steps, the course grid. If you can save a factor of 2 at least, or so, or even a bit more, then this can still lead to some improvement.
It's just if I do a ballpark estimate, so you have 3,500 M, your grid spacing is say 1 M, there's an order of magnitude, it's 3,000 points in one direction, but in the angular direction you only need 40 or 20 or points. It sounds like not very much to me if you compare that with say 200 cube grid, which very quickly, but I believe you of course, if you say it's low.
Yeah, I mean, the effect is of course, it's not that pronounced. I mean, it's not a big speed up, but it's still.
It's worth doing for the hassle of coding.
Even 30% are, I mean, worth it. In the end, because we have no CCE, we don't actually need to go to a radius of 1000 M. So at that time, when we did the first simulation of multiblocks, we didn't have CCE yet, and we simply analyzed the waveforms at 1000 M, and of course now you can drastically get rid of have this coordinate stretching much earlier, because you can already extract at 100 or 200 M or even further in with CCE, transport the signal to scribe, but I will talk about that.
So another thing here, so your wavelength is actually a few hundred M, yes?
I mean, in the inspiral, the wavelength
yes.
Yeah, but during merger, and especially the higher modes, you'll have a much, I mean, the higher the M, the higher the frequency. I mean, L4 has twice as high frequency as L2, N2. S6, M6 3 times.
So there is this the rule of thumb that for fourth order difference, you need about 50 bit points per wavelength or so. So you may be doing fine. This is what I'm wondering. Even with your stretch grid, I don't know what is the accuracy of your radial evolution, but you probably use 6th order or 8th order.
No, 8th order.
So you may be doing fine even in the course radio.
Actually, we have also tested because, I mean, if you have 8th order stencils, of course we need more points for the boundary patch interpolation. We have a larger ghost zone between the patches. Interpolation is rather expensive because it doesn't parallelize that well. You have to collect all the coordinates from all the different processors and everything, especially if you have 1000 processors, that can be quite a hassle. And I've tested it with by simply applying only 8th order on the finest grid and 4th order everywhere else. Essentially, I didn't see a difference at least in the non-spinning equal mass waveform. The dynamics, the puncture tracks were really identical, and the waveforms as well. Of course, again, for higher harmonics, you can see that it's a bit noisier. I mean, amplitude and especially if you compute instantaneous frequencies and stuff like that, then it will have influence. All right, so these are actually the waveforms. So here we have psi4, this is L2, M2, up to L8, M8, and here we have plotted the amplitude of each mode respectively, and also the instantaneous frequency. And okay, L8, M8 starts to look very noisy in the inspiral, simply because the amplitude is too small, but still during the late inspiral and plunge phase and merger and the ring down, it looks, I mean, you still have something that can be used, although we were not able to verify convergence here for this L8, M8 mode simply because the angular resolution that you have to also decrease for the CaJAGWR runs couldn't capture this mode anymore. But for example, the A6, M6 mode, you still get convergence in that. So interestingly, these instantaneous frequencies. Not interestingly, I mean, it's a well-known fact that during ringdown, this must settle to the quasi-normal modes of the black hole, and we have actually tried to fit a constant to this frequency to see how well this agrees with a perturbed Kerr black hole. And this is a zoom in now for the L2M2, L4, M4, and L6, M6 mode, and we have fitted here these lines and found a remarkable agreement to, within our numerical accuracy, which is given here by these numbers, to the quasi-normal modes that we find in the literature, especially the ones given by Berti et al. This one Berti paper. And yeah, so we can say that within our numerical accuracy we can identify these modes as
what do you use for the spin parameter?
the final spin of the apparent horizon.
But determined from the mode frequencies? Or
No, determined from the isolated horizon, on the apparent horizon, and the mass, of course, is also from the isolated horizon from the reason.
What is the accuracy you get for the imaginary part of the frequency?
Actually, that I haven't looked at.
Okay, because we tend to get an order of magnitude worse agreement.
Yeah, actually, when I 1 year ago, 2 years ago, actually, when I first looked at it with a not with a multi-patch code, but simply at the L2M2 mode of some Cartesian-based code only, yeah, it was harder to.
It's usually more difficult.
It's more difficult. Yeah, so now we have achieved a larger simulation domain, larger extraction radii, but still our extraction radius is finite, so we don't know what the error is, because extrapolations don't tell us what the error is. We can only tell the error if we have some solution to which we can compare this. And so the only way out is to actually compute the full nonlinear dynamics of the spacetime out to square plus, so to compute the waveform from the metric in the neighborhood of square plus. And that can be achieved by using characteristic evolutions, which are a certain formulation of the Einstein equations along null arrays, or null hypersurfaces. And this can be achieved by making use of the Bondi-Sachs framework, which uses retarded time coordinate u, and which basically uses here these null hypersurfaces, and an area radius r, and of course angular coordinates xa. And the nice thing about this is that this scheme allows radial compactification without making the scheme inaccurate. And that enables us to place future null infinity on the computational grid. And the drawback of this method, so you could ask why don't we just use characteristic evolutions for binary black holes for the entire space-time. The problem with characteristic evolutions is that caustics may form, so light null arrays may intersect. That means we have a coordinate singularity there, but coordinate singularities are also bad singularities, and we want to avoid that, of course. The way out of this, so characteristic evolutions, therefore, is only really suitable for the far wave zone, where we are safe with these coordinate singularities. Coordinate singularities can, in principle, there are ways out of that. One can treat these coordinate singularities, but that's not implemented. And the way out of this is to use the Cauchy evolutions, which I described a few minutes ago, still for the interior domain around the black holes, and then just attach a subsequent characteristic evolution to integrate the Einstein equations to square plus. And this can be done by dumping metric data here on some world tube during Cauchy evolution. And this metric data on this world tube can then use as inner boundary data for the characteristic evolution, which then transports the signal radially outwards to square plus. And this wave that we obtain here at square plus will then, of course, be free of any finite radius effects. Plus, it will also be free of gauge effects because we transform to the desirable Bondi gauge at square plus.
So I have a question here. So So one thing that was still ambiguous in this construction is the initialization of the first null hypersurface. And the way we used to do that is just roll it off in some arbitrary way. And so have you ever looked at effects of choosing that in more than one way?
Yeah, so what we usually do here is to just impose conformal flatness along, so we just put the metric deviation from sphericity, this variable j, which Peter knows, we put this to 0, which means it's conformally flat with respect to this foliation here. This will coincide only at that point with conformal flatness here on this initial hypersurface here on the Cauchy evolution. But of course here it will generally deviate, especially also because there will be an inconsistency in the initial data placed here and the initial data placed here, because as soon as we let the Cauchy evolution go, of course we have also initial data here, especially some spurious wave contents due to the conformal flatness assumption on the initial hypersurface. That will of course also travel again back inwards, and at some point will hit this initial characteristic hypersurface, for which we have already imposed different initial data, and that will be some inconsistency. But we will show later on that within our numerical accuracy, this doesn't affect us yet, but at one point it will hit us. I mean, if we increase the resolution further and further, we must see eventually the inconsistency here between these two parts of the spacetime. So practically, this procedure is done as follows. So we have here one Cauchy hypersurface, then we have here the world tube gamma, on which we dump our metric data, and this world tube is built up by coordinate spheres with some angular coordinates, which are simply on the Cauchy side theta phi and theta phi coordinate system. And then we construct the normal vector to the spatial hypersurface, the normal vector with respect also to the metric, to the space-time metric in this hypersurface, to this coordinate sphere here. And from this we can construct outgoing null vectors, which induce our outgoing null geodesics, parameterized by some Fn parameter lambda. And this, the union of all these outgoing null arrays will then be the null cone in which we solve the characteristic equations. And in order to get the metric, so here we have the metric in terms of our AEM variables, we have this 3+1 formalism, but we need to transform it to boundary data in terms of the Bondi metric data, and that can be achieved by first by applying Jacobian transformations. The trouble is only that the Bondi metric makes use of an areal coordinate radius, which can only be defined once we have the metric in terms of this Fn coordinate system with the angular coordinates of this Fn coordinate system here, this null array coordinate system. And so that means that we first apply the Jacobians, transform the metric to this Fn coordinate system, and then afterwards we can define the areal radius, and then we apply another coordinate transformation to get the Bondi-Sachs metric in a neighborhood of gamma at the world tube. And this can then be used to present it to the null code, and the null code can integrate these boundary data onto square plus. And we have implemented this as a post-processing tool. So first we just run the Cauchy evolution scheme, which doesn't know anything about any characteristic evolution except for the fact that during the simulation we dump metric data on coordinate spheres to disk, and then after the Cauchy evolution is completed, we just take the data, read it in the characteristic code, and perform then the characteristic evolution to get the answer in Scribe, to integrate the field equations onto Scribe plus. And especially particularly we dump the metric, so the free metric, gamma ij, the lapse and shift, in terms of spherical harmonic modes. And that has two advantages. One is data compaction, of course. We don't have 2D data, but just the harmonic modes. Then we can cut off at some point. I mean, we have to, in any case, we have to cut it off, but we can select some LNM mode in which we cut off the expansion, and that means that you can filter out high frequency noise. Plus, the main advantage really is that we can easily transform to different angular coordinate systems, because the characteristic evolution uses stereographic coordinates, whereas on our coordinate sphere, for simplicity, we just use a polar spherical coordinate system with just one coordinate patch. So the first thing we did then was to check age invariance of the scheme. So we just put on the Cauchy side just a Schwarzschild solution, which is static, so it cannot contain any gravitational radiation. And then we just applied some coordinate transformation, which shifts the Schwarzschild space-time back and forth about the origin, and there should be no gravitational wave signal generated by this. And when we apply the CCE technique, actually that's what we see. So here you still see some non-zero signal. Of course, it's numerical error. Hopefully it's numerical error. And in fact it is, because if you increase the resolution by a factor of 2, this decreases by a factor of 4, the error, and that's shown here, so it converges. Here, in contrast to this, where we just use the finite radius extraction sphere on the Cauchy side, we see that there's a small amplitude, and it's not convergent. By increasing the resolution, we don't see any convergence of this error here.
So even though it's not convergent, they are the same magnitude for the coarse grid, essentially.
Actually, I think here it's 10 to the minus 4, and here it's 10 to the minus 8.
Oh, I couldn't.
The thing here is that here at Scry we always measure R psi 4, whereas here we have just psi 4, and if we have an extraction radius of 100 m or so, we have to divide the amplitude by this essentially. So.
Right. So for a realistic grid size, which error is smaller?
I can't tell you right now. But let's go to real binary black hole simulations, then you will see that the error is pretty small in the wave extraction. So we've also looked at the constraints. So the Bondi system gives rise to 3 constraint equations, which are contained in the Ricci tensor, so R00, R01, and R0A, contracted with one of the diet components that represents the spherical metric. And we see second order convergence at the world tube of, for example, R01. Here we only see first order convergence of R00 at Scry plus, but then I also must say that currently in the code, in the transformation from the Cauchy metric to the characteristic, to the Bondi-Sachs metric, there's one component that is only first order accurate. So there's a certain variable which was so that you have to do some expansion in terms of R, and the second the first radial derivative of that quantity is only known to first order. Could influence this. And yeah, the other component is a very similar behavior. Just select these ones.
So do you know that the first order, so the dominant error is not angular, but it's some other type. So if you look at the surface class of the error on the Scry class, is it smooth in the angular dimensions?
It's pretty smooth, yeah.
Okay, so it's not a high frequency angular first order noise that you have then?
No,
Because there is no kind of discussion on that.
Mm-hmm. I should look. I mean, I think maybe I was not very. I mostly focused really on the norms of these constraints. I didn't do much 2D data analysis. Could be that I missed something, but as a first glance, it looked okay to me, the data. So, of course, we've discussed this problem with the inconsistency of the initial data, for example. So we would like to see estimate the error that you make when you just pick a different world tube location. So you have a simulation, you have one world tube at r equals 100, let's say, and then you have a different world tube, r equals 200, for example, and at each of these world tubes, you can attach a characteristic evolution, completely different, of course. You have one characteristic evolution for the r equals 100 metric data, and you have one evolution for the r equals 200 metric data. And in each of these two characteristic runs, you get out waves, of course. And ideally, the difference between these extracted waves should be 0. Of course, due to numerical error, that's never the case. So what we did is we just performed a CaJAGWR resolution run on the Cauchy side and a fine resolution run on the Cauchy side. In each of these runs, we dumped metric data once at r equals 100m and once at r equals 200m. And then we just looked at the difference between these waveforms, between the two world tubes, and the error must converge to 0 if you increase the resolution. And that's in fact what we see here. So this the red curve is the final resolution run, and this is scaled for second order convergence. Okay, here some spurious spikes, but I think they reduce to first order if you just do that for rescale it for first order. Anyway, during merger, it mostly looks like second order, and most of the time it looks like second order. And if the initial data were inconsistent, then this would show up actually in this test here, because ultimately, if you crank up your resolution to infinity, there must be some difference simply because the initial data is different. And but fortunately, with no numerical accuracy here, we don't see that. And actually, the differences in the waveforms between these two different world tube locations of the order of 0.03% in amplitude and a dephasing of 0.002 radians, which is extremely small.
How many orbits are there before merger?
Something like, I think, 8 or 9 orbits. So then, very important question is, of course, how does the result at square plus differ from a wave extrapolated to infinity? And here you see psi4 plotted against each other. So you have the blue curve is the CCE curve, the CCE wave, and the red one is the extrapolated wave. I mean, first glance, it's identical. Of course, it's not really identical. It's not to high accuracy. It's not identical. If you look at the differences, you will find that there's a difference of 0.2% in amplitude and a dephasing of 0.01 radians in phase, which is 1 order of magnitude larger than the error between the two different world tube locations. And also, interestingly, this error here is already of the order of magnitude of numerical error in current binary black hole simulations. So that means, in total, that eventually your simulation is not, your accuracy is not limited necessarily by the resolution around the black holes, but also by the fact that your extrapolation induces an error which is a systematic one and which doesn't converge away. And by the way, this extrapolated wave used detectors at 6 coordinate spheres. The innermost was at 280 m and the outermost at 1000 m, and the extrapolation itself is therefore already pretty accurate. Most other groups can do that at between 100 and 200 m.
Do you know if the numerical error of the CCE waveform was dominated by the numerical error of the Cauchy evolution or of the characteristic evolution?
The error is dominated by the Cauchy evolution.
So you don't need a very accurate characteristic indice for what you're saying?
The error, if you take the difference in the world tube locations as a measure of the error in the characteristic evolution, you see that and compare that to the error and the dephasing in two different resolutions coming through different resolutions on the Cauchy side, you will see that the error is much larger. In other words, if you take the waveforms that you have generated via characteristic evolution and just do a 3-level convergence test with these waveforms, by essentially, by changing the Cauchy evolution resolution, you will basically only see the error coming from Cauchy evolution. So you can directly you can take the finite radius waveforms, get the phase out, get the amplitude out, do a convergence test, you will get the same convergence exponents as if you would have also done a characteristic evolution.
So how many linear points you needed for that characteristic evolution?
So here, regular, so for the high-res run, I took like 480 points and angular points 60 per patch.
I see, so it's not that one.
No. So anyway, the message here is now that the CCE wave, unless we hit this limit with the inconsistency of the initial data, will contain only discretization error, whereas the extrapolation, of course, has a systematic error which will not converge away. So you can also ask, does it matter for gravitational wave detectors actually the difference in the two waveforms? And you can make use of these methods. You can calculate the detector noise scalar product of the difference of the two waveforms, one extrapolated waveform and one obtained at CaJAGWR+. There's a certain technique which is described in this Lindblom paper, which first computes the match between the extrapolated waveform and the waveform at CaJAGWR+, where you first compute the match between two given waveforms, and then given the phase that maximizes the match, you construct the difference in the time domain of these two waveforms. And then there's the condition that the scalar product weighted by the detector noise must be smaller than 1, then you can't distinguish these two waveforms for parameter estimation. And the outcome is that for the current ground-based detectors, so to make it a bit more clear, the scalar product can always, this value of the scalar product can always be rescaled because the waveform, of course, depends on the distance to the source. I mean, the amplitude will be larger if the source is closer by, and that means you can always rescale this scalar product to be less than 1 if you choose a distance that is sufficiently far away. And this distance is given here, and for the ground-based detectors, so LIGO and Virgo, this is the numbers. I mean, the waveform will only be distinguishable up to 5 megaparsecs, which is essentially nothing. I mean, there are no significant event rates in that radius, the volume of space-time surrounding us. And for the advanced detectors, the distance will be already 1 order of magnitude larger, but still, I mean, within this distance, probably the event rates are still not significant, given that nothing has been measured yet. And for LISA, this will be visible to up to approximately z equals 1. So,
is that for a particular fixed angular direction, or did you average over?
Oh yeah, here I took the L2M2, just the L2M2 mode, and yeah, I mean, because then yeah, right.
So I guess the message here is that for detection purposes, the non-processing cases can be extrapolated at just enough vectors.
Yeah, so I mean, unless you want to do extremely high precision, I mean, no, with the current detectors, yeah, I mean, it doesn't make any difference. Extrapolation is just as accurate as the CCE wave. In other words, because the error between CCE and extrapolated waves is already on the order of the discretization error, that means in turn that the discretization error essentially would, if you compare two waveforms with resolutions large enough, would essentially result in the same numbers. And,
but this was for equal mass non-spin?
yeah, that's only equal mass non-spin.
Did you consider the calibration errors in the detectors when you were thinking about this? Did you consider the calibration errors in the detection when you were thinking of this? Because that could make it even more insignificant.
Yeah, no. I mean, we just took the noise curves that are published on websites and just idealized. I mean, probably it's even worse. I mean, this is all idealized. I mean, it's probably even a bit more insignificant. So anyway, we've also checked conservation of energy and conservation of angular momentum. And the takeaway message here is that computation in square plus and extrapolations will to very high or to the similar accuracy conserve these conditions here. So you always must have that the initial AEM mass of the spacetime must equal the final mass of the black hole plus the emitted gravitational radiation, and that's always the case to very high accuracy for extrapolations and computations in square plus. For a finite radius extraction without any extrapolations, this error is always much larger. So for example here this finite radius, the error here in the angular momentum is in the order of 10 to the minus 2, whereas for CC it's on the order of 10 to the minus 4. But since we're running out of time, we just get to more interesting stuff. So we have then applied this code, the multi-patch code, and the CCE extraction technique to actually get a measure on the nonlinear memory in binary black hole mergers. And the memory effect is sourced by the emission of gravitational radiation, and especially the interaction with themselves was first described by Christian Reisswig in 1991 and by Blanchet and Damour independently in 1992. And this mode is a non-oscillatory gravitational wave component, which depends on the entire past history of the space-time, and it induces a permanent displacement of the space-time. So if you start initially from 0, in the end, the waveform will not return to 0, but will return to some constant but offset, some non-zero offset. So the dominant contribution of this nonlinear memory effect is given by the L to M0 mode, shown here. So it's monotonically growing, and during merger will rise significantly. And then there will be also the ring down signal from the L to M2 M0 excitation of the black hole modulated on top of that. And then afterwards, the space-time has encountered some displacement. And if you reconstruct the waveform for at some angle where the y to 0 spherical harmonic is non-zero, you will see that here you have the dominant L to M2 mode essentially, which oscillates about 0 and in the end doesn't return to 0 here, but levels off at some non-zero value. And this effect is difficult to measure. So if you just use finite radius extraction, you will have influence from finite radius effects and gauge effects, and summarize the systematic errors. And it's very hard to disentangle any drifts or anything that arise due to these systematic errors from the actual physics. And as an example, I've plotted here 3 different L to M2 modes. Essentially, I compare here extrapolation against CCE. The CCE result is given here by this curve here, which is monotonically growing. It's essentially the same plot that I've just shown. And then I've done here extrapolation on a set of different radii to infinity. So I've computed psi4 on these finite radius extraction spheres, extrapolated psi4 to infinity, and then integrated it in order to obtain h. And the inner set of radii that I used was using detectors from 100 to 200 amps. And as you can see, the curve is completely screwed. So there's nothing that you can. I mean, it's very hard to see anything from that. This is essentially just crap. And if you use larger extraction spheres, the result will be better, but still it's closer to the answer in square plus, but still there's some other error or remaining error due to the finite radius and gauge effects. Then we have looked at the dependence of the memory in terms of the 2D parameter space of equal mass and spin aligned binaries. In this parameter space, you have equal mass, and you have only the spin component that is aligned or anti-aligned with the orbital angular momentum. That means you only have 2 free parameters, which can vary between -1 and +1 for each black hole. And what we find first of all is that the memory, so this offset, it only depends on the total angular momentum of the space-time, so it's parameterized by the initial configurations which go along the diagonal from -1, both spins pointing down, to +1, both spins pointing up. And memory is largest for maximally aligned spinning black holes with this configuration, and it's smallest for these configurations. And interestingly, it's constant for all configurations that have equal spin but opposite sign of opposite direction of the spin. So here you see plotted the L2 M0 mode, and they're all on top of each other essentially. And if you look at the dependence, so if you compute the difference between that value and that value here, or the displacement from zero essentially, and this offset initially here is, in our case, is given by some fit to PN expressions. We find in the end that the total memory can be modeled by some quartic polynomial. And here this red curve is some comparison to an expression derived by Mark Favata, which I believe is only really valid for non-spinning black holes. This is this expression here, which relates.
I think it would be valid for. I think that particular. I think that expression on the bottom, H and N, in terms of the energy radiated, would be valid for spinning holes, but I think maybe you have to include the sum of the 2, 0 and 4, 0.
Okay. In the radiated energy? Or?
Yeah, that's right.
Okay. But in our case, we always include the radiated energy from all modes. And okay, so this is an expression here. So the red points are derived from this expression, which relates the memory to the total radiated energy from the black holes. And it agrees fairly well. Okay, it slightly under predicts it, but seems to work fairly well. An interesting point really is that the ring down is much stronger pronounced in models that have spin down. So the memory is smaller, the total displacement of spacetime is smaller in these models, but the ring down has a much larger amplitude, and that can be explained maybe by the fact that binaries with this configuration here suffer some orbital speed up, so they inspiral much quicker than this configuration, which suffers some orbital hang up. But this means that the speed up means that the radial motion is relatively larger compared to the tangential motion, which is closer to a head-on collision in some sense. And for head-on collisions, we know that the L2 M0 mode is very large. And this would explain why the ring down is excited much more in these particular cases. But that has interesting implications for when you try to observe that in gravitational wave detectors, because the ring down frequency and amplitude is of course then much more visible or will be much more visible in the gravitational wave detector. For example, what I plotted here is the frequency spectrum of the different models along this diagonal where you parameterize the binaries with the total spin, which is equal in sign. Because due to the much stronger ring down signal, the curve here, so this is for example the curve for this guy here, which has a smaller memory amplitude, but the ring down amplitude is much larger, you will get significant contributions also in the higher frequency regime, so that the overlap with the detector noise curve is much larger, which then of course results in higher signal to noise ratios. So essentially you measure, because the ring down, you always measure essentially the ring down in these cases, because the ring down is much stronger, you will have a larger signal to noise ratio for these modes. For example, the opposing case, where you have the orbital hang-up, the spin up, because the ring down amplitude is so small, you essentially will have this curve just goes almost down linearly here in this dot plot. Essentially, you only see the very low frequency components of the memory effect itself, of the non-oscillatory mode itself. And yeah, so I think, okay, this is pretty idealized because we will never measure in a gravitational wave detector a single L2M0 mode alone. It will always be superposed with other modes, and
this is the ring down only into 0.
yeah. I mean, no, it's the entire mode, but because the ring down frequencies have a much higher frequency than the very low frequency drift, or not drift, but this very low frequency growth of the memory itself, we will essentially always see the ring down signal.
No, is the 2-2 mode included there?
No. It's really only idealized. It's
Yeah.
just to get a feeling for
Yeah,
how well
okay.
these numbers shouldn't be taken seriously, but at least gives a feeling for how things behave. Yeah. Interestingly, of course, is that the L2M2 mode in the orbital hang-up case has many more cycles in the high amplitude regime, and then therefore it generates a much larger signal-to-noise ratio, and so it's just contrary to the L2M2 mode. And finally, you can also ask yourself, okay, has this actually any influence on matched filtering searches? Because usually you only take the L2M2 mode and try to match that against your detector signal. But we have seen that for certain angles, the L2M0 mode has some significant contributions. So, because the waveform really visibly levels off at some, or oscillates to some, rings down to some non-zero value, does this waveform, if you really use this waveform compared to just the dominant L2M2 mode, which doesn't have this offset feature here, but which will simply return to 0, if we compare these two waveforms for matched filtering searches, will this make any difference? So in other words, I just sum all the L2 modes together at an angle where the 2-0 mode is non-zero, and compare that to just a wave signal that only contains the L2M2 mode, and try to get a match from, or compute the match or mismatch of these waveforms. And the answer is that mismatch for the mass ranges that we have considered here for that model is always much smaller than 10 to the minus 5. So 10 to the minus 5 is really the maximum, and that means that essentially the memory doesn't have any influence on these on template bank constructions. All right, so to summarize everything, so I've talked about multiple codes which can give you improved resolution for the waves, and which allows one to extract higher modes, and also modes that are causally disconnected from the artificial outer boundary. Also essentially for CCD that is important because you want to eliminate this influence as well. So the boundary data that we generate on these world tubes is causally disconnected from the outer boundary. So we have, I've talked about the unambiguous gravitational wave extraction and shown that this is gauge invariant, and shown that current numerical relativity waveforms are all right, essentially. I mean, the extrapolations are very accurate. And then I've used CCE to evaluate the nonlinear memory mode L2M and M0. and found that the nonlinear memory, the total offset of the space-time, depends only on the total spin and has a maximum in this configuration here. But as opposed to the dominant L2M2 mode, this configuration, which has the smallest offset, memory offset in the end, but the largest ring down, will be most visible in gravitational wave detectors due to the ring down, and the memory will not have any notable influence on match filtering searches, such as if you include this mode. Yeah. Thank you very much.
Hi. So, Christian Reisswig, are there any additional questions? I know we were all asking a lot of questions during the talk. All right, let's thank Christian.
And there's wine and cheese in the main kitchen on the other side of the building.